Hello, my name is Eduard Iban, and I will present you a polynomial kernel for line graph deletion, which is a joint work with William Lechette from University of Bergen, Norway. Line graph deletion fits into a bigger framework of graph modification problems, where in a graph modification problem, we are given a graph G, integer k, and the question is if we can modify G using sequence of at most k allowed operations to obtain a graph with some property p, where the allowed operations could be vertex deletion, edge addition, or edge editing, which is deletion or addition, and the property could be graph being edgeless, having no cycles, being planar, being a so-called H-free graph, where in this sense we mean by H-free that it doesn't contain any graph if in some family H as an induced subgraph or a line graph. And I put both H-free and line graph in red because the line graph is our result, and it actually is also H-free for some finite family H. And depending on the allowed operation, we get different variants of the problem. We get vertex deletion, edge completion, and edge editing, where our work is in this paper is about edge deletion. The other word in the title was polynomial kernelization or kernelization. So kernel or a kernelization algorithm is a polynomial time algorithm that takes as an input graph and some integer k, and in polynomial time it outputs an equivalent instance of the same problem that is much smaller. Equivalent meaning that if this is a yes instance, then the result is also yes instance, and small meaning that the size of the output graph plus the parameter k is at most some function of k, where this function g is called size of a kernel, and we are often interested in polynomial kernels, where which just means that we want G to be polynomial. Just to mention some related work. In related work, of course, there is plenty of work on different modification problems, because this is really very general framework. But we will focus only on related work on H-free modification problems, where H is some fixed set of forbidden use subgraphs, and in particular on kernelization of these problems. Okay, so H-free vertex deletion is known to be NP hard whenever H contains at least one graph with two vertices, and it is known that it admits a polynomial kernel. The situation is much different for edge modification problems. Namely, P versus NP dichotomy is still unknown, and Arvid et al. Only recently gave a dichotomy in the case that H contains precisely one graph H. Kraj and Wallström in 2013 gave first graph H on actually 7 vertices, such that H-free edge deletion and H-free edge editing does not admit the polynomial kernel unless some standard complexity theoretic assumption in the area fails. And later Kai and Kai showed that this is not really an exception but more of a rule, by giving real large family of graphs for which H-free edge modification problems do not admit polynomial kernels unless the same assumption. And at this same ESA, Marx and Sandeep studied also H-free modification problems, and besides other results, they also conjectured that if H has at least 5 vertices, then H-free edge deletion has polynomial kernel if and only if H is complete graph or has at most one edge. And they also backed this conjecture by giving a list of 19 graphs of 5 and 6 vertices that needs to be resolved in negative way, such that this conjecture is true. And given this conjecture, and also some other results that I don't mention here on kernelization of a graph of size at most 4, last graph of size at most 4 that is still unresolved is CLAW, or K13. This is actually a relatively long open-standing problem, and several researchers studied some subclasses of CLAW-free graphs. Tsigan et al. In 2017 gave a kernel for CLAW and Diamond free edge deletion, which is actually precisely edge deletion to line graphs of a triangle free graphs, and we basically extend this result to line graphs of any graph. Okay, so what is a line graph? Line graph of some graph G is a graph LG, where the L of G, where the vertices of the line graph are precisely the edges of the graph. So if the black was our graph, then the vertices of the line graph would be the red vertices, and there is an edge between two vertices of the line graph if they corresponding edges share an endpoint, right? So with this given graph, we would get line graph that looks like this, and we will say that the graph is a line graph if it is a line graph of some graph G, where we don't need to know what the graph G is. We study then the line graph edge deletion, where we are given a graph and an integer k, and we ask whether we can delete at most k edges from the graph, such that the resulting graph is a line graph. And our main result is that the line graph edge deletion admits a kernel with at most O of k to the 5 vertices. Now, before we get to our result, I need to mention the following structural result on the line graphs. So it is known that the following three statements are equivalent. First, G is a line graph. Second, the edges of G can be partitioned into cliques, such that no vertex lies in more than two of the cliques. And of course, since it's the partition of the edges, no two cliques share more than one vertex. Okay, so let's take a look on our previous example. So we have this red is a line graph, and we can actually construct this clique partition if we know the underlying black graph. For example, what we can do is we take a look on the vertex of the underlying graph and put all the edges that are incident to this vertex into one clique. So like this. In this way, we get something like this, and we can see that every vertex of the line graph appears only in two cliques, that are cliques that corresponds to the vertices of the edge that corresponds to this vertex. And the other characterization is characterization by forbidden induced subgraphs of G. So it's known that G is a line graph if and only if none of this below 9 graphs is an induced subgraph of G. And for our proof, or at least for the sketch in this talk, the only important thing about these 9 graphs is that all of them have at most 6 vertices, and that this one graph is one of them. This is exactly k5 minus an edge, right? So having this structural result about the line graph, let's have a look on the general agenda of the proof. I will first tell you all the steps that are needed to obtain our kernelization algorithm, and then I will come back to each of the steps and say how we obtain them. So the first step is to actually find some set of vertices S that is small, of size at most 6k, such that if we remove it from the graph, then we obtain a line graph. And moreover, even if we put back any single vertex in S back to G minus S, we still have a line graph. Now, using this characterization by partition of the edges, we, as a second step, partition the edges of G minus S, which is line graph, into cliques in a way that are given by this characterization, so that in a way that it is really a partition of the edges, so every edge appears in precisely one clique, and no vertex appears in more than two cliques. Just note that clique partition witness, or the set of the cliques, might not be unique, and in particular for vertices that are in only one clique, we can add a singleton, and also we can remove singletons from this partition. But it doesn't matter for our proof. Having this, we now look at the cliques in C. So we look at the cliques in the clique partition witness, and we show that the cliques of size at least k plus 7, so large cliques, do not contain any edge in the solution. And this allows us to split cliques into small and large cliques, and actually now be concerned more about interaction of the solution only with the small cliques. Now, based on this distinction between small and large cliques, we actually define kind of a notion of a distance, which will distance from S, so from the deletion set, which will not be really a distance in a graph, but it will be kind of a distance only through small cliques. And because it will be distance only through small cliques, we'll be able to bound the number of cliques at some given distance by k to the d, or O of k to the d. And note that every clique, also the large cliques, will be at some distance, so will be assigned some distance. Only how we compute the distance depends only on the small cliques. Now, having this, the other step would be to bounding actually a distance of a small clique that can contain a solution edge. It will actually not be that in every solution, but we will show that there exists a solution such that only small cliques that are close to S interact with a solution. And we show by this that we can actually remove all the edges in the cliques that are further away. And after removing this, we will see that we have only O of k to the 5 or something like this cliques, or O of k to the 4 cliques. And we will show, this will help us to show that we can actually bound also the sizes of the large cliques. Okay, so let us go through the proofs now, step by step. So the first step is actually relatively simple. We will just use the forbidden induced subgraph characterization, and what we will be doing, we will be greedily packing edge or non-edge disjoint forbidden induced subgraphs, meaning that two induced subgraphs are disjoint even if they share exactly one vertex. Right, and we will just, since the largest induced subgraph has of size 6, we can enumerate all the subsets of size 6, and we can find all the forbidden induced subgraphs, and we can find some greedily pick maximal induced maximal packing of these, and put all the vertices in this induced subgraph to S, and we can see that we couldn't find more than k disjoint forbidden induced subgraph, because from each we need to remove at least one edge. So this is how we obtain S, and of course, if putting one vertex back to G minus S destroys the property that a graph is a line graph, there will be a forbidden induced subgraph containing only this vertex in S, which would be packed, so it's not possible. second, to obtain the partition, we just actually use the algorithm by De Giorgi and Simon to decide whether the graph is a line graph. And they actually do it by constructing underlying graph of a line graph, and during their construction they basically construct the click partition witness. So this we basically get by free by just taking their algorithm. Okay, so this brings us to the third step, and to the bounding the size of a click in C that can contain a solution. Okay, so let's take a look on some large click in C, in the click partition witness. And let's assume that there is an edge that is in some optimal solution, or actually not necessarily optimal, but that is in a solution of size at most k, right? And let the solution be A. And let us take a look on all the edges of A that are inside C, including this one edge. There are at most k edges in A, and because click is large, it might not be, the following might not be completely clear why it works for k plus 7, but if you can definitely see why it works for like 4k plus 7, and you have to trust me why it works also for k plus 7, is that we're able to find a triangle such that none of the edges in the triangle are removed, so none of them are in A, and none of the edges between the triangle and these two vertices is in A. But then this graph here is actually K5 minus an edge, and this is one of the forbidden induced subgraphs from the characterization, which means that this couldn't happen, and we couldn't remove any edge from C. Now we actually show something a bit stronger, meaning that actually this click C will be a subclick of some click in the click partition witness, in any click partition witness for a solution for G minus A, or A is some solution of size K. And this is because since we don't remove any edges in here, and this click is very large, the only way how we can partition the edges in this click in a way that every vertex appears at most two clicks is by taking the whole click. And note that actually this is true already if size of the click is at least 4. Okay, now we can define the level structure and the distance. So we can first think about S as basically zeroed level, and all the remaining levels will be just partition of the clicks of the click witness. To define the first level, we need the following lemma, which says that for every vertex V in S, there are at most 6 clicks, such that the neighborhood of V in G is covered by the 6 click and S, and also all the edges in the neighborhood are covered by the 6 clicks and S. And the reason why this is basically because putting V back to G minus S results still in a line graph. We get that V is in that line graph in 2 clicks, and if it actually in some large click, that large click has to be covered by 1 click in C in here, and if it's in the click of size at most 4 including V, then this click might be covered, actually this triangle might be covered by at most 3 clicks in C. Right, so having this, we can let the first level to be at most 36k or 6 times size of S clicks that cover the neighborhood of S and actually all the edges in the neighborhood of S. So it looks something like this, and just note that there might be a click that contains a vertex in the neighborhood of S and noded L1, but it doesn't contain an edge in the neighborhood. And now, given first I levels, we construct the I plus first level by taking all unassigned clicks, so all the clicks that are not in the first I levels, that have a vertex in some small click in Li in common. Now, because every vertex appears in at most 2 clicks, and we only take the small clicks of Li, it follows that there are at most than in Li plus 1 are at most k plus 6 times more clicks than in Li, and we get the bound on the number of clicks at a given level. And now we say that click is a distance d from S if it is actually in LD, right? And note that in this step we add also large clicks in Li plus 1. We just then don't consider them when we are constructing Li plus 2. Okay. Now, to bound the distance of a small click that contains a solution, and also actually at the same step, we will show that removing edges covered by clicks at distance 5. We actually show the main result of our paper, and that is that there exists an optimal solution A for G, and a click partition witness CA for G minus A, such that for every click C at distance at least 5, it holds that C is precisely in CA. Right, so the clicks at level 5 will stay exactly the same, which allows us then to remove all the clicks at distance 6 and even modify a clicks at distance 5 to be just singletons. Okay, so the first step is to understand the interaction of distance 4 clicks with an optimal solution. And there are 2 things that we need to understand. Is first, what about a click in a solution, or in the witness for a solution that intersects click C in C in an edge, has to be actually a subclick of C. This is the first thing that we show. And the second, that no 2 non-singleton clicks in CA that are subclicks of the same click at distance at least 4 intersect. Okay, so let's first take a look on the first part. So one thing is, take a look at some click at distance at least 4. Take a look on edge xy, and take a look on the vertices that are adjacent to both x and y. Since this click is at distance at least 4, none of these vertices is in S. So all of these vertices has to be at distance at least 3, or in a large click, but this is not very important for us. Now we can actually show, because all of these vertices has to be in G minus S, we can actually show that only one vertex can be adjacent to both x and y and be outside of C1. And moreover, this vertex cannot be adjacent to anything else in C1. Which then shows that the only bad thing that can happen is that in the solution witness there is a triangle like this that intersect C1 only in an edge. We call such triangle bad triangle. And what we show is that, by a relatively technical proof, is that there is an optimal solution without any bad triangle. And the situation with bad triangle is like this. So we have this click C1 containing xy, and we have to have click C2 and C3 that contains z, such that z and x is in C3 and z and y is in C2. And if the solution contains x, y, z, click x, y, z, and we denote X, Y, Z, the other clicks containing X, Y, Z respectively, then we actually can see that big X has to be subset of C1, C3, and so on. And having this, we can actually show that we can replace this solution by a solution that contains in each CI some subset of CI that contains intersection of Y with C1 and X with C1 plus some other vertices, in order to not have clicks that intersect this click in two vertices. Using this result, we can actually now take a look on the click and two subset of a click that intersect in one vertex, and obtain the same, that we can actually replace it by other click that contains both, and it actually gives us a better solution than this. And combining this, we actually get the main result that we wanted, and that is that we can keep the clicks at levels at least 5 intact. And as I already mentioned, having this, we can remove all the edges at level at least 5. For every vertex that is on intersection of level 4 and level 5, we introduce a singleton. And this gives us instance that is actually equivalent. Note that since we only keep clicks up to level 4 plus some singletons, there are only k to the 5 vertices in the small clicks at this point. And now only what we need is to keep at most k plus 7 vertices in every large click. And now if we have some vertex that is in two large clicks that are both larger than k plus 7, we can just remove it. And by greedily removing this, we will actually end up with at most k to the 5 vertices as well. Okay, so just to conclude, we present the first polynomial kernel for line graph edge deletion, which actually resolves open problem posed on Worker in 2013. The existence of polynomial kernel for line graph edge completion and edge editing still remains open. And also note that we only consider line graphs of a graph, but there is also notion of a line graph of a multigraph, and the kernelization of edge modification problems for this problem remains open as well. And our result can be also seen as a kind of a step towards the claw-free edge deletion, which still remains widely open, and there are still several other interesting subclasses of claw-free graphs that might be interesting to study. Thank you for your attention.